So I want you to imagine something for a second. If you were to take the digestive enzymes that are currently, sitting inside your abdomen right now, and you just drop them directly onto a raw steak on your kitchen counter.
Oh, wow, starting with a visual.
Yeah, well, I mean, those enzymes would literally dissolve that meat into a liquid, pretty much entirely,
Absolutely would, yeah.
right? But here's the wild part. The organ that is manufacturing and storing those highly corrosive chemicals, it is itself made entirely of meat.
It is basically a biological paradox.
Exactly. And that is what we are digging into today. We are pulling back the curtain on the pancreas. We're using a really comprehensive Wikipedia article as our guide to try and understand this hidden dual-purpose powerhouse.
Which is an organ I think most people barely think about.
Right. I mean, think about the last meal you ate. Without you even realizing it, this single salmon-colored organ has been running this incredibly complex chemical laboratory. And our mission today is to figure out how it quietly orchestrates our digestion and our cellular energy and, how it keeps us alive in the face of all these shifting demands.
It's doing so much heavy lifting behind the scenes.
Okay, let's unpack this, because to understand what the pancreas actually does, we first really need to understand where it hides and how long it took humanity to even figure out it was in there.
Yeah, the pancreas is, well, it's a master of evasion, really. Physically, we are talking about this 12 to 15 centimeter kind of salmon-colored lobulated mass.
Lobulated meaning like bumpy?
Yeah, exactly. Kind of bumpy and uneven. And it is tucked deep, deep in the retroperitoneal space.
So way in the back of the abdomen.
Right. It sits entirely behind the stomach. The head of it is sort of nestled right into the C-loop of the duodenum, which is the first part of your small intestine. And then the tail stretches all the way across the upper abdomen to literally touch the hilum of the spleen.
Which explains why no one could find the thing.
Exactly. Because of that sequestered location, early anatomists just completely missed its significance. They thought it was just a cushion or something.
Yeah, the source mentioned it took until roughly 300 BC for the Greek anatomist Herophilus to formally identify it.
And even then, it didn't get its modern name for a while.
Right. Later on, Rufus of Ephesus gave it the name we use today. It comes from the Greek words pan, which means all, and kreas, meaning flesh. So literally all flesh.
Which is honestly a perfect description of its appearance. I mean, unlike the liver or the heart, it doesn't have a distinct firm capsule around it, doesn't have a heavily muscular structure at all.
It's just sort of this soft, unstructured mass.
Yeah, it looks like a somewhat amorphous, solid chunk of glandular tissue, but you really cannot let that soft appearance fool you.
Because of the blood supply, right?
Yes, exactly. This organ draws a massive high-pressure blood supply directly from the splenic artery and the superior mesenteric artery.
Which tells you it's doing a lot of work.
Huge amounts of work. It's a real testament to the immense metabolic load it carries every day.
The whole structural dynamic really makes me think of, it's like a highly effective but completely reclusive backstage stage manager at a theater.
Oh, I like that analogy.
Right? Because the heart and the brain, they're always taking center stage. They get all the glory. Meanwhile, the pancreas is entirely in the shadows, wearing a headset, silently running the pyrotechnics, the lighting, and the trapdoors, so the whole production doesn't just, collapse.
That analogy holds up perfectly, especially when you realize this stage manager is simultaneously running two entirely different shows at the exact same time.
Because it's doing digestion and blood sugar.
Exactly. And the reason it handles two completely unrelated physiological duties stems directly from its frankly chaotic organogenesis.
Meaning how it forms in the womb.
Right. When an embryo develops, the pancreas doesn't simply grow as a single, neat little glandular unit. It actually originates as two completely separate outpouchings from the developing foregut.
Wait, two totally different pieces?
Yeah, you have a ventral bud and a dorsal bud. They start off physically separated.
So how do they become one organ?
Well, as the embryonic digestive tract elongates and kind of rotates, that smaller ventral bud physically migrates. It rotates all the way around the gut tube to meet the larger dorsal bud. And then the two eventually fuse into one single mass.
That sounds like a lot of moving parts that could easily go wrong.
Oh, the mechanical precision required for that rotation is astounding, and yeah, it absolutely leaves room for error.
What happens when it messes up?
Well, if those two buds fail to properly fuse their internal duct networks, the resulting condition is called pancreas divisum.
Divisum, like divided.
Exactly, leaving the patient with basically two separate drainage systems. And worse, if the ventral bud fails to migrate completely and instead it wraps around the foregut during
It
development,
creates a ring.
right, it creates an annual pancreas, it effectively places a physical chokehold on the duodenum.
Yikes. So it's basically strangling your intestine.
Pretty much. But the structural origin explains those anatomical quirks, sure, but the functional division is what really stands out when you read the source material.
Because it is a fused organ, so the labor is split.
Yeah,
But the ratio is just incredibly skewed.
it really is.
Like 99% of the pancreatic tissue is purely exocrine, which means it's dedicated entirely to digestion.
Right.
And only 1%, literally just 1%, is endocrine tissue, which is tasked with managing all of your blood sugar hormones.
And that tiny 1% is the sole barrier between you and fatal metabolic collapse.
Okay, I am going to push back heavily on that evolutionary design.
Oh, really? How so?
Well, dedicating a mere 1% of an organ to blood sugar regulation seems like a catastrophic biological vulnerability. I mean, think about a single heavy meal. Say you eat a massive plate of pasta. That sends a torrential flood of glucose into your bloodstream.
Oh, absolutely. A huge spike.
Right, so relying on just a few microscopic clusters of cells to pump out enough insulin to handle that massive systemic wave, it seems like trying to put out a forest fire with a garden hose. Why would human physiology bottleneck something so critical into such a tiny physical footprint?
What's fascinating here is that the endocrine pancreas doesn't function like a storage tank at all. It functions as a highly calibrated, extremely high-speed sensory network.
So it's about sensors, not volume.
Exactly. We are talking about the islets of Langerhans, which are these tiny little clusters scattered all throughout the exocrine tissue. They don't need physical volume because of their vascular architecture.
How does the blood flow work for them then?
These islets are fenestrated. That means their capillaries are highly porous. They're like a sieve. The beta cells inside are practically bathing directly in your blood.
Oh, so they're just constantly tasting the blood.
Exactly. The millisecond that glucose levels rise, the beta cells depolarize and dump insulin directly into the systemic circulation. They rely on sheer speed and receptor sensitivity, not sheer mass.
So the small footprint is actually an advantage. It allows for immediate systemic distribution rather than relying on, like, a bulky, slow-moving endocrine gland.
Precisely. It's highly efficient. But the sheer volume of the exocrine system, that remaining 99%, that is equally impressive when you look at its daily output.
Yeah, that 99% is a chemical factory running at absolute maximum capacity.
It never really stops.
The source notes that the acinar cells in the pancreas produce 1.5 to 3 liters of pancreatic juice every single day.
That is a massive amount of fluid.
3 liters. That fluid is continuously dumped through the major pancreatic duct right into the duodenum, and it serves two distinct, frankly brutal functions: neutralization and cellular dismantling.
Right, so let's look at the neutralization first. That relies heavily on bicarbonate.
Because stomach acid is so intense.
Extremely intense. The chyme, which is the partially digested food leaving the stomach, is fiercely acidic. The pancreas has to buffer that acid immediately to protect the delicate intestinal mucosa.
Otherwise, it would just burn right through the intestine.
Exactly. And to achieve this, the pancreatic ductal cells utilize something called the cystic fibrosis transmembrane conductance regulator, or the CFTR gene.
Wait, cystic fibrosis? That's the same gene involved in the lung disease, right?
Yes, exactly the same one.
Yeah.
This is where the cellular mechanics get brilliant. The CFTR channel basically pumps chloride ions out into the duct lumen.
What does that do?
That creates an electrochemical gradient. This gradient drives a specialized exchanger protein to swap those chloride ions for bicarbonate.
Ah, okay, so it's pulling bicarbonate in.
Right. And then water just naturally follows by osmosis, which creates this high-volume, highly alkaline fluid that neutralizes the stomach acid.
Okay, so once the pH is stabilized and it's safe, the second component of the pancreatic juice can finally get to work: the enzymes.
These dismantlers.
Exactly. The pancreas secretes amylase to cleave complex carbohydrates into simple sugars, and then lipase to break down triglycerides into free fatty acids.
But the most dangerous secretions, by far, are the proteases.
Right, primarily trypsinogen, which are designed to just tear apart dietary proteins.
They're the ones that could dissolve the raw steak.
Yes, going back to the steak on the counter, this is where the biological failsafe kicks in, which I loved reading about. The acinar cells manufacture these proteases in an inactive precursor form called zymogens.
Right, they aren't active yet.
I visualize the zymogens as having heavy plastic safety caps like childproof packaging locked onto their chemical scissors.
That is a great way to picture it.
So the pancreas ships them out completely inert. They travel safely down the duct without dissolving the organ itself.
They remain completely inert until they physically cross the threshold into the duodenum.
And then what takes the caps off?
Waiting for them on the brush border of the intestinal wall is a localized enzyme called enterokinase.
Enterokinase.
Yeah, enterokinase acts as the key. It cleaves a specific peptide bond on that trypsinogen we mentioned and instantly transforms it into active trypsin.
So it's like pulling the pin on a grenade.
Exactly. Trypsin then initiates a massive proteolytic cascade, basically snapping the safety caps off all the other zymogens in the area. The digestion only happens where the anatomy is actually equipped to handle it.
Okay, so the 99% has done its job. It has dissolved the meal. And now a massive tidal wave of glucose, fatty acids, and amino acids is crossing the intestinal wall and hitting the bloodstream.
And this is the exact moment that tiny 1% has to wake up.
Right. The islets of Langerhans take over. And within these microscopic islands, there's a strict division of labor.
Very strict.
You have the alpha cells, which secrete glucagon. And glucagon is like the mobilization hormone, right? It signals the liver to undergo glycogenolysis, breaking down stored glycogen into glucose to raise blood sugar.
Right, glucagon pushes sugar into the blood, but on the other side of the equation, you have the beta cells.
Secreting insulin.
Exactly.
Yeah.
And rather than just acting as a simple key like we often hear, insulin functions much more like a bouncer at an exclusive club.
A bouncer? How so?
Well, it binds to receptors on the surface of muscle and adipose cells. This triggers a whole intracellular signaling cascade that forces these special transporter proteins called GLUT4 to literally embed themselves into the cell membrane.
Oh, wow. So they build a door.
Yes. Only then can the glucose molecules cross the velvet rope and enter the cell to be burned for ATP.
And moderating this entire tug-of-war are the delta cells. They secrete somatostatin, which acts as this localized inhibitory hormone that suppresses both insulin and glucagon, just to prevent, chaotic oversecretion.
It acts as the referee. And the synthesis of insulin itself is a total masterpiece of quality control.
Because the beta cells don't just instantly materialize active insulin, do they?
No, not at all. The ribosomes on the rough endoplasmic reticulum first translate this really long amino acid chain called pre-proinsulin.
Pre-proinsulin, that's a mouthful.
Right. Then a signal peptide is chopped off to form proinsulin, which then physically folds onto itself and gets secured by these strong disulfide bonds.
Like tying a knot.
Pretty much. Finally, inside the Golgi apparatus, an enzyme excises a middle section of the molecule called the C-peptide.
Taking out the C-peptide is like snipping the plastic rings off a six-pack of soda so the individual cans can finally be used.
Exactly.
What's left is the mature, active insulin molecule packaged into these secretory granules, just waiting against the cell membrane for the signal to deploy.
And the medical community remained entirely in the dark about this intricate hormonal dance until late in the 19th century.
Oh yeah, the Minkowski experiment?
Right. In 1889, Oskar Minkowski was conducting physiological experiments, and he just surgically removed a dog's pancreas.
Which seems kind of wild.
It was a different time for science, but he observed that the dog began urinating copiously, and this is the crazy part, the urine was actively attracting flies.
Which means it was full of sugar.
Exactly.
Minkowski had inadvertently induced severe, sudden-onset diabetes, proving the pancreas was the thing regulating the unabsorbed sugar.
But the actual isolation of the hormone took another 3 decades. Frederick Banting and Charles Best finally managed to extract active insulin from the islets in 1921.
Huge breakthrough.
Massive. And if we connect this to the bigger picture, the control mechanisms governing these beta and alpha cells extend far beyond just sensing the glucose from your latest meal.
The nervous system gets involved, right?
Yes, the autonomic nervous system plays a massive regulatory role. Under acute stress, sympathetic nerve fibers release norepinephrine that actively stimulates glucagon secretion and inhibits insulin.
Wait, it stops insulin?
Yeah, because the biological imperative is clear. Keep glucose in the bloodstream for immediate explosive muscle use. You're stressed, you need energy now.
Fight or flight.
Right. Conversely, during periods of rest, vagal nerve stimulation from the parasympathetic system promotes insulin release, shifting the body into anabolic storage mode.
Here's where it gets really interesting, though. Reading the source material, I was just struck by the paradoxical reaction the pancreas has to pure protein.
Oh, the amino acid response.
Yeah. When you consume a heavy protein load without any carbohydrates, the rush of amino acids into your blood triggers the beta cells to release insulin, but it simultaneously triggers the alpha cells to release glucagon.
It seems entirely counterintuitive to release antagonistic hormones simultaneously, right?
Yeah, they fight each other.
But it is actually a critical survival mechanism. The insulin is absolutely required to facilitate the uptake of those new amino acids into your muscle tissues for protein synthesis.
So you need the insulin to build the muscle.
Yes. But without any incoming dietary carbohydrates, that insulin spike would rapidly clear the existing glucose from your blood, plunging you into severe hypoglycemia.
You would just pass out.
Exactly. So the simultaneous release of glucagon forces the liver to dump stored glucose, which perfectly offsets the insulin's hypoglycemic effect while the amino acids are being processed.
That is just brilliant. The entire system is an incredibly high-stakes, real-time balancing act between these corrosive digestive enzymes and delicate life-saving hormones.
It really is.
And because the physiological margins are so razor-thin, the clinical pathologies associated with the pancreas are just devastating. When it breaks hard.
The most immediate and violent pathology is acute pancreatitis.
Right.
This occurs when that zymogen failsafe we talked about is breached. Whether the primary pancreatic duct is obstructed by a migrating gallstone or the acinar cells suffer direct toxic insult from chronic alcohol abuse, the trypsinogen becomes prematurely activated inside the pancreas.
The safety caps come off too early.
Precisely. The organ literally initiates a cascade of autodigestion. It breaks down its own vascular and cellular architecture.
That sounds unimaginably painful.
It leads to massive inflammation, excruciating retroperitoneal pain, and potentially lethal systemic inflammatory response syndrome.
And then we have the metabolic failures of the 1%. Diabetes mellitus.
Right.
Type 1 diabetes is characterized by absolute insulin deficiency. It's an autoimmune cascade, often triggered by a combo of genetics and environmental factors that results in the complete destruction of the beta cells.
And this is where that C-peptide test comes in. In type 1, the C-peptide we discussed earlier drops to practically zero.
Because they aren't making any endogenous insulin at all.
Exactly. Exogenous insulin administration shots or a pump becomes immediately mandatory for survival.
But type 2 diabetes presents a completely different timeline.
It does. It typically originates as peripheral insulin resistance. The muscle and adipose cells basically stop responding efficiently to the insulin bouncer at the door.
They just ignore the bouncer.
Right. In response, the beta cells undergo hypertrophy. They physically enlarge, churning out massive sustained waves of insulin to just force the glucose inside.
But they can't do that forever.
No. Over years of this hypersecretion, the beta cells suffer severe oxidative and endoplasmic reticulum stress. They simply exhaust their secretory capacity and undergo apoptosis. They die.
And the source notes several pharmacological interventions for type 2. Medications like sulfonylureas, they mechanically force the issue.
How so?
Well, they bind to ATP-sensitive potassium channels on the beta cells, closing them. This depolarizes the cell membrane, causes calcium to flood in, and physically forces the release of more insulin granules.
It just squeezes the sponge.
Exactly.
Yeah.
And we also have incretins, like GLP-1 agonists. These mimic the natural hormones released by the gut to amplify insulin secretion, but only when glucose is actively being absorbed.
Which is much safer. But honestly, the most lethal clinical challenge remains pancreatic adenocarcinoma.
Pancreatic cancer.
Yes. This malignancy originates almost exclusively in the ductal epithelium of the exocrine pancreas, frequently localized right in the head of the organ.
I found myself hung up on a very specific clinical reality while reading the source on this.
What was that?
Well, a human being can survive a total pancreatectomy. If the organ is completely removed, the patient can theoretically manage by taking oral enzyme replacements with every single meal and carefully managing an insulin injection regimen.
That is true, yes. It's tough, but possible.
So if the organ itself is functionally replaceable by modern medicine, why is pancreatic cancer so uniquely devastating and lethal compared to other operable malignancies?
That is a great question. The lethality is deeply tied to its insidious anatomy. The tumor proliferates in the retroperitoneum, completely hidden from physical palpation.
Right, you can't just feel a lump from the outside.
Exactly. Furthermore, the pancreas is tightly interwoven with major vascular structures and a very dense lymphatic network. By the time a ductal adenocarcinoma grows large enough to actually provoke symptoms, it has almost always micrometastasized to the liver or surrounding lymph nodes.
It spreads silently before you even know it's there.
Yes. And the delayed symptomology is chilling. Patients frequently present with vague abdominal pain, unexplained cachexia, which is extreme weight loss, or painless jaundice.
Why jaundice?
That jaundice occurs specifically when a tumor in the pancreatic head expands enough to physically compress the common bile duct. It literally blocks the pipe, backing bilirubin up into the bloodstream.
Wow.
And because of this late presentation, the source notes that only 10 to 15% of these adenocarcinomas are candidates for surgical resection at the time of diagnosis.
Just 10 to 15%? That is brutal.
It is. For advanced cases, the medical approach pivots to aggressive chemotherapy.
Right, regimens like FOLFIRINOX.
Yes. FOLFIRINOX is a heavy cocktail of 4 different chemotherapeutic agents. It's designed to disrupt cellular curves compared to older single-agent therapies.
But the prognosis remains overwhelmingly poor.
Right. It remains a profound medical challenge. The pancreas is robust enough to process a lifetime of heavy metabolic loads, yet fragile enough to be destroyed by its own cellular products or aggressive ductal mutations.
It's so delicate. But stepping outside of human pathology for a minute, the source material explores how pancreas exists in the rest of the animal kingdom. And the evolutionary variations are wild.
Oh, animal biology gets really weird with this.
It does. In teleost fish, which represent the vast majority of fish on Earth, the pancreas doesn't even exist as a solid, distinct organ.
What is it then?
It's just a diffuse web of glandular tissue scattered across the mesentery, liver, and spleen. Lampreys just feature localized pancreatic nodules embedded directly into the wall of their intestines.
That is bizarre.
Avian anatomy is equally strange. Birds can possess up to 3 entirely separate pancreatic ducts draining into their digestive tracts.
The evolutionary plasticity of the organ in nature really stands in stark contrast to its rigid, fragile nature in humans.
Definitely.
But I think the most jarring contrast is actually found in the culinary world.
Oh, you're talking about sweetbreads.
Yes. In classical gastronomy, the pancreas of a young calf or lamb is a highly sought-after delicacy. In high-end French cuisine, if you order riz de veau or sweetbreads, you are being served a pan-seared pancreas.
Which is just wild to think about.
It really is. This raises an important question. How does an organ entirely packed with potent proteolytic enzymes capable of dissolving muscle tissue? How does that become prized for its incredibly delicate, rich, and tender flavor profile?
The irony is hard to ignore, isn't it?
Mm.
The exact same anatomical structure that we handle with such profound medical trepidation, the organ prone to catastrophic autodigestion and aggressive silent malignancies in humans, it is casually soaked in milk, sautéed in butter, and served as a gourmet appetizer.
It perfectly encapsulates the duality of the organ, really. It is a harsh, chemical environment wrapped in an unassuming, delicate physical structure.
So what does this all mean?
Well,
I think the takeaway from this deep dive is just a renewed appreciation for the physiological tightrope your body walks every second of the day. The pancreas is wearing its backstage headset right now.
Yeah.
It is constantly monitoring the chemical makeup of your blood, microdosing hormones to sustain your brain function, while simultaneously manufacturing biological scissors to dismantle your next meal.
And all while keeping the safety caps firmly in place so it doesn't destroy itself.
Exactly.
It is a remarkable hybrid factory. It's basically an evolutionary compromise that fuses 2 completely unrelated biological mandates into a single space with absolutely zero margin for error.
Which leaves me with one final provocative thought. We examined how this organ initially develops as 2 separate embryonic buds that migrate and physically fuse together, right?
Right, the ventral and dorsal buds.
One mass basically dictates the 99% exocrine chemical path, and the other quietly runs the 1% endocrine blood sugar network. They were 2 functionally distinct organs crammed into one anatomical package.
Stranded together, yeah.
So given the extreme evolutionary timeline of human physiology, I'm talking millions of years into the future, could the human body eventually correct this chaotic organogenesis?
Oh, that's an interesting idea.
Could we evolve to a point where the pancreas successfully splits into 2 entirely distinct organs, permanently separating the corrosive digestive factory from the delicate hormonal thermostat?
A total unfusing.
Exactly. It makes you wonder what the human anatomy of the distant future might look like, and if that invisible backstage manager will, finally get a room of its own.